Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome to the NPTEL online certification course on structural systems in architecture. So, we are in the module 7 and the module 7 is all about the tensile and the plate structure, and this is the second lecture on the tensile structure. So, today we are going to discuss in the 32nd lecture as the membrane structure. So, as you know that in the membrane structure we have introduced a bit in the last class or the last lecture. So, in today we will go into deep into that, and the concept will be covered. Today's lecture will be we will start with the introduction and then we will do some numerical problems on catenary. If you remember, last lecture we did some numerical problems of funicular polygon, and we will discuss about the basic forms of the membrane structure and also the support systems. So, the course objective, the learning objective will be we will outline the structural concept of the membrane structure, and we will illustrate the types, parts and the functions of the membrane structure. Membrane structure are very common. If you see the historically, this particular type of structural systems has been adopted in the peoples in the different areas. There is a photograph of teepee, that particular house, kind of a traditional house of in northern plate of America. They made that particular type of house in by the animal skin is called teepee. And as you know, the animal skin are of membrane, so that kind of a tent can be done through that. And the next picture is the very recent picture. If you go to the Jaisalmer, the desert of Rajasthan, the tent for tourists are also made by the membranes, kind of a canvas kind of a, or the cloth, basically a thick cloth kind of a thing. So, now the thing is that as we understand, membranes can be used, or that they are the human civilization using this particular membrane for quite a long time. So, our goal will be the how we will provide the cable, because the membrane cannot actually stay. So, you need to cable to make them tie, and you have to make it straight and stretch it properly, and with that we can create the roof or maybe some wall or so. So, the points of the column support or maybe the internal mast or whatever has to minimize, that is one of the fundamental goal, and we have to also see the profile of the membrane, and the profile of the cable that going to support the membrane must be such a way that it should actually do not cross the limit of its stress or whatever. So, if you now see in the nature, there are also membrane structure. We can found it from the net that was formed by the spider, and if you very minutely see this particular spider net, you can find out there are primary cables which actually going to support act as a support in this particular cases, the membranes. So, these are the typical point where the supports has been made to the leaf or maybe the stem of the tree. Those are the primary cables. Those are then the primary cables. Maybe this one is also a primary cable. It is also having some kind of a secondary cable which are connected to the primary cable to increase the stiffness, but this arrow is a bit wrong position. I mean to say these are the secondary cables which are connected to the primary cables radially. Here it is radial. So, this is a primary but these are all secondary cables which are going to connect the primary cables. And finally, there is a spiral member also in it. Those are act as a membrane. So there are cables like this, there are spiral cables like this. Those are actually creating this kind of a membrane structures. So see how beautifully they create this particular cable formations, or the total structural formation based on the two set of cable and one set of the spiral membrane cable also. So catenary we have already discussed. A catenary curve can be as presumed, or that can be assumed to be a curve which can be created by the own weight. So a membrane structure, when it is a thin membrane kind of a thing, is supported by the cable, it has to be very flexible, and it will be actually sag because of its own weight. So it is actually go with a catenary shape. Now catenary shape can be described very easily. Suppose if I go to a small video, then we can actually understand this better. So this catenary curve, you see, a chain can be act as a catenary, because it's actually it is actually fundamentally this shape comes from its own weight. No external weight actually has been introduced over here. This is the chain, a gold chain. It's form a catenary shape. This shape is called a catenary shape, and it's because of its own weight. Another very interesting thing is that in this catenary if you see it, I will explain, the loading intensities are quite fundamentally going to be densify as you go to the support. So this is one hand is the support, this another hand is another support. So if you go towards the support, the loading intensity will be magnified. And another very important thing is that, suppose if I restart these things from here, when the span is larger, the sag is smaller, and when the span is smaller, this is very large. This particular the sag is very large. So this is the one of the explanation of the catenary. Now let us go to some of the numerical examples on catenary. So as the catenary shape is a mathematically can be established with some kind of equation form, and in a catenary, suppose this is the origin, that is the 0 point, this is my x axis, this is my y axis, and these two are the support. See both the supports in the same level, and at this particular, this is the cable that is hang like that, and I take one point in the cable which is point xy, and which is at a distance, curved distance. This is the distance of the particular arc, or this particular point, the portion of the chain S, that is the curve length, and this is under the loading, and this loading are very there is if you take the uniform each weight of the each millimeter or each centimeter, this uniform distributed loaded are now gradually densify towards the end, and because of that the shape is going to form. And the equation of the catenary is can be given like this. This is the equation where y equal to a cos h means the hyperbolic cos x by a, where x and y are this coordinate, and a is given as the T naught by rho a g, and rho is the density of the chain or the thread or the cable, a is the cross section of the cable, and g is the acceleration due to gravity, and T naught is the horizontal component, the tensile force, which is any horizontal, which is going to be constant, for this is your T naught, constant for everywhere. There are T naught can be found out by the omega into a. Omega is the loading intensity, which is nothing but your this rho a and g, which can be converted into Newton or maybe kilonewton per meter. There are some other equations are also with this catenary, that S, this the curved length, the actual length of the cable from the bottommost point, from this point, is your a sine hyperbolic sine x by a, and the y square equal to s square by s square. This a is a very tricky thing. The a is actually, if you see the a is a distance from the tip of this catenary to the origin. This is the a. This particular distance is the a, and a has to be defined or the measure by this. Now, next is you can also find out the tension in the cable with this particular formula, because if you take the free body of this cable, see this cable is under three load. One is this the horizontal tension, one is the tension in this inclined portion of the cable, the end portion of the cable, and this is the W into A. W is the loading intensity and S is the length. So, it is total weight of the cable of that particular part. So, that comes in a triangular the force geometry, and from that force geometry I can find out what will be the, either you can use this formula or maybe you can use this formula to find out the tension of cable at any particular point. Any particular point can be determined either by s or by y, because y changes as per the coordinate changes and s changes also, the distance changes, so the length of s is also going to change. Now, the hyperbolic sine and cosine functions can be given with this particular two formula, with exponential x plus exponential plus or minus minus x or so. But in the calculator we can also find out there is a hyperbolic button, and from that if you start with that hyperbolic button first and then go to sine, it goes with the hyperbolic sine, and then put the actual the whatever may be the angle, and then equal to gives you the value. Or if I sometimes go, if I have to go to the inverse function of the hyperbolic sine or cos. So, then before you go to this sine, you go to the shift and then come back to the sine, and then your this thing, and then this. So, I have a small video, because sometimes we had a problem with calculator to find out the how to do this particular calculation in the calculator. So, I have a very small video on that also. So, you take the first switch on, and then you go to the this hyperbolic, and then go to the sine or cos or whatever, and then put the values and then equal to. So, you will get the sine hyperbolic too. You clear it, and then you go to the hyperbolic. Suppose you want to do the cos now, give the values and then equal to, then cos h is 4 is that. Then if you want to do the inverse, then go to there and then go to shift and then give the sine inverse, then and then 1.2 is equal to this. And similarly, if you want to do the cos inverse, so hyperbolic, then go to there, cos inverse, and then put the values and then put it equal to. So, like that you can use the calculator also in the hyperbolic function mode. So, in from here let us go to solve some problem. So, I have a catenary which has a length of the cable length is 120 meter. That means, this total the cable length is 120 meter, and the span is 100 meter like this, and the density and all these things I have mentioned. I have to find out the sag, that means how much is the h I have to find out, and the T max and T minimum. So, here I first find out how much is the omega, that is the force, or sorry, the intensity of the loading, that is 0.8 kilonewton per meter. And what I do, I first use this equation S equal to A sin h x by A. S for a half span means this much of span. I know the x value is your 50 meter, half of 100, and it has the S value of this value is half of 120 meter, that is 60. So, put the S equal to 60 and x equal to 50. Now, we have to solve this particular equation by hit and trial method. That means, you put some values of A and just try whether it is coming 60 or not. So, I will start with S equal to 60, A equal to 60 equal to that S. Start just imagine, I mean starting point, I got S value is 56. I have to use the calculator for that, and gradually 56 is not going to be 60 equal to that this part. So, I have to change this A equal, it is 60. So, I take 55, I got S equal to 57.5. My target is 60. Again I go back to 47, then I got 60.9. It is very close to 60, but still I am not very happy. So I go for 47, a equal to 47. I got 59.97, which is very close to 60. So I say that a equal to 47. So it is a trial and error you have to do. Now as I got the a equal to 47, now I use the second equation, y square equal to a square plus s square. The y square is equal to 47 square plus 60 square, 60 because this is 60 or 60, and y I found out, this y is I found out then 76.216 by virtue of this equation, and y is, what is y? Y is a plus sag h. So the sag is equal to y minus a, so I find out this 29.126 meter will be the sag. If this is 100 meter and this total length is 120, the sag will be your 29.216 meter. Similarly, I can find out the T max as the omega, that is 0.8 into y max is 76.216, 60, and T mean equal to omega into a, that is 0.8 into 47, that is 37.9 kilometer. So I have another problem where I already given the value of sag as 22 meter. I don't know how much is the span, but the length of the cable is 150. So this is 75 and this is 75. So total is 150. So I can directly now use this formula where y is equal to from this to the topmost point. I mean in this case. So this is 22 plus a square equal to a I don't know, a still I don't know, so plus 75. So I try to find out how much is the a is 116.84, and as I know a, I use this equation, I put the values of a and I try to find out the value of x. S I know as 75, so the x equal to a into sine inverse s by a. That is why you also require sometimes the inverse function to calculate from the calculator, and I put the value of a and also the s, and then find out the x equal to 70.62. That means your span is twice of that, 141, because x is this length, x is your this length, sorry. So it is 72, and also I found out the T max and the T minimum by virtue of the omega into y max and the omega into the a. This is a, and y max is your a plus sag 22. So now let us go to some of the basic forms of the membrane structure. In the basic form of the membrane structure, as there are 5 such forms can be made. There may be some the hybrid type of form also can be made, but in general there are hyper, the conical, the wave, the arch, and the cushion. The hyper form is like this. It is anticlastic kind of a surface, as you know, it is anticlastic. So there are 2 different curvature, and the terminating point should be placed in different levels. So what happened is that in this anticlastic formation can be made. See, these 2, one is this and another is this, are in down, and other 2 are in opposite the top level. So that will give you a formation. See here, these 2 are in down and these 2 just next are in the top. So that kind of a formation can be made by, and that if it is made, it is called hyper type of the membrane. Then the conical, in the conical it is synclastic kind of a form where both the curvature in the same side and the Gaussian the curvature is positive, and this in this case you see what happened is the terminating points are placed at the bottom level. So it placed in the bottom level, and there is a ring, and it will be actually connected to this particular ring. So this is the ring, and all other points are in the some bottom level, and this flows like that. So this is the kind of a conical kind of a the membrane structure. The next one is the wave. Wave is a type of you can say it is an array of the some of the shell kind of a thing, and it's not hyper. It's if it look like a hyper because these two are on the bottommost level and two are on the topmost level, but these two are not the next two. This should be the other way around. So, and it flows in a typical formation like that. So, this is one unit and this is another unit like that, or maybe it can be wavy also. This the next one will discuss the arch. So, sometimes you can go with the arch form and then we can create some kind of a wavy kind of a nature also. The next one is the arch form, where a arch has created with stiffened member. Suppose this sometimes the arch has been created one after another arch, but those arch are truss, the steel truss, and those steel truss are creating some kind of a stiffening kind of a attribute to the overall structural systems, and then over that you create a kind the membrane. So, it will be now going to be arch. At the end arch, there are sometimes a middle arch, and then you provide this kind of the membrane. And due to the sometimes this formation is the arches are like this. So, this is a kind of synclastic, or sometimes if the arches are like this and then on a different plane it is moves like that. So, you can have a set of arches of two different directions. Then it can be also create a anticlastic kind of a scene, kind of a the profile. And the last one is called the cushion. Cushion is mostly used in the air inflated kind of a pneumatic kind of a structure, where it's a thick kind of a membrane and there are less number of support, and this particularly as it is air inflated, it is actually very light and it can retain that particular shape by the air pressure itself. So, if I see if I take a flat panel membrane, just like a see, suppose it is a handkerchief kind of a thing. So, raising two opposite corner of can create a hyper, and raising the middle part of that particular the handkerchief and placing the outer perimeter below a certain level with respect to that central level is going to give a conical, and the introduced a series of curvature and clamping edges and all those kind of a phenomena or structural supports if you provide in the edges and series of those in a symmetrical order. So, you can create the arch form or the wave form. So, let us now discuss the some of the support systems of a member. Suppose this is a typical sketch of a tensile member. So, we have lot of cables is required because those membranes cannot actually going to support by its own. So, you require some of the cables, or sometimes you require some of the rigid truss members also. It is not always not the cable. So, if I go with a cable support system, so there are mast which is actually ground the force, and as all know that we have discussed in the last presentation is that the mast are in compression. So, there are maybe definitely one which is main mast, there may be few more. So, those are the edge mast, or sometimes we may say it is a secondary kind of a mast. So, this edge mast is sometimes act as some kind of a anchorage or something like that, which will going to have some kind of a anchorage to a particular set of cable. Now, those are the mast, and second set of the cables, that is one is the main cables are the, suppose this cable is the suspension cable, this is you can say it is a stay cable or gay cable, and based on these two primary cables which are there are maybe some 2-3 more secondary type of cable because of your to take care of your formation. So, there are ridge cables which is give you some kind of the effect of a ridge, and there are some kind of a splice cable which is actually going to change the typical slope of one part of the membrane to the another part of the membrane by virtue of wide angle changes or so. So, you need this kind of a splice. So, those are the splice cable, and a particular stabilizing cable is also required. Sometimes of course it is not full, this particular has to go to this particular some of the edge mast or the some of the main mast. So those are the stabilizing cable. Because of a suspension cable alone may not take that particular load because of the too much of cantilevering thing or so. So you require another stabilizing cable from the behind to just to give a kind of a additional kind of a support. So there are some of the photograph I have taken from internet of different buildings which is under the membrane structure. So this one marked 1, these are the mast, central mast, then there are the suspension cables which connected the mast to the end, and then there are fabric membrane follow the suspension cable structure also. So there are some small examples I also taken down from the internet. The sources are given in the right hand side below. So this is not by cable, this is by truss. See, this is the bus stop or parking lot. You can use this kind of the interesting kind of a scenario or this kind of a structure which are supported by the tubular truss, and then the in between two tubular truss there are a stretched member of the membrane. This is another very interesting to see is that this is a the membrane is actually connected in between two cantilever. You can say it is a column, you can also say it is a beam. It's flying from the ground and then go with a parabolic way or non-linear way. It's converting from column to beam, and those are spaced or placed in some distances, and the stretched member of the membrane is covering that. So these two are the typical you can use for any kind of parking lot or any kind of bus stop also. This is a conical kind of a shape, which inverted conical type of membrane group. What we have discussed here is conical is the it is an inverted version of that, where the ring, this is the these are the rings, which rings are upward, and the end portion of the membrane was in downward in that case, but it is a conical is reverse conical, and there are the main suspension cables are flying like this, and how beautifully it can be arranged such a way that it looks like a lot of trees and it can cover the arena. The another one is that the same type of the design or the same scale of the field or maybe the space can be covered with a membrane structure. But very interesting thing is that this membrane structure is actually going to there is a edge support by triangular truss member, triangular truss member at the end, and this is the central mast, you see, and this is that ring, and central mast is not continuing till the ground, it is hanging, it is the suspended central mast. Very beautiful way it has been, and this particular from the central mast the cables are attached. And so finally, who is taking the load to the ground? It is this particular part of the truss member which finally supports the load and grounded the load by this is the column. So it's a real wonderful combination of a three-dimensional linear kind of a truss, triangular kind of a space frame. It's not a very huge space frame, but it's a kind of a truss, you can say, a triangular kind of a 3D kind of a truss, and that is grounded by inclined truss or that triangular truss, and finally the cable. But interesting thing that I found here is that the mast is hanging. So I have taken the reference from those books. This Timoshenko and Young is a engineering mechanics book. I have already told you that particular book is you can say it is a Bible in engineering mechanics. So that particular books also cover a chapter on the catenary and the funicular polygon. So I have taken help from that, and there are some other books also. So in conclusion, I must say that the membrane structure is as just like act as a skin to the building. It's actually going to cover the building as a roof, and also some of the peripheral walls also skin. It's actually a kind of a form active kind of a structural systems. The cable are hang freely here and wrapped with the stencil fabrics, and due to that it gives you a kind of a the hanging or the freely suspended profile. It is definitely an excellent solution for the long span architecture. So in the next lecture we will go to the last part of the tensile structure, that we will do some more numericals and also the applied form of numericals on tensile structure in architecture, and we will also discuss some of the real life examples of the tensile structure by some famous architects. So I have one homework for you. So the cable of length 100 meter, the actual length of the cable is 100 meter, is fixed at 2 point of same level. Suppose this is 2 point and this is your cable. So this cable length is your 100 meter. The load intensity is 0.5 kilonewton per meter. So the load intensity omega is your 0.5 Newton per meter, and to find the T max and T mean if the sag is your 10 meter, 20 meter or 30 meters. So this sag is changing. The first case it is 10, the second case 20, and third case 30, and you find out all those. You find out the span. In this case, what will be the span? If you remember this particular small video, you see the span changes, the sag changes. So I kept the sag, 3 sags, and then find out the span, how much is the span, and also find out the max and mean of tension, which is actually going to occur in the lowest point, the minimum tension, and the highest point at the support, it will be the maximum tension. Draw the graphs showing the changes of the respective values of with respect to the sag. So you have to draw some of the curves. Suppose this is the span and this is the sag, how it is changing from that, and also for T max and T mean, that how it is changing in case of these 3 changes of the sag, you have to find out. Thank you very much. That's the end of the lecture number 32.